Hello. Okay, so this is our fourth video, I believe. Today I'm going to start my personal least favorite topic, which is vectors, because it's often the most confusing for a lot of students and also for myself, actually, when I was a student. So, I think for vector problems, the first thing to keep in mind is to not overthink it, which by which I mean, um, for other kinds of topic, let's say let's say trigonometry, let's say complex numbers, let's say functions, I think it's really easy to form a very systematic understanding of the topics. And in fact, a lot of these topics just all bridge together into a one big mathematical thing. But I think vectors is a very unique topic, or rather it operates on a very different part of your brain, and I feel like for a lot of students it's a really let's say dangerous territory, or rather it feels like a very different place to be. But that's not true. Obviously, vectors have the unit has to do with your system of equations. It has to do with matrix reduction, and that in turn can relate to your complex numbers, to functions and polynomials and all that. So I'm not saying that vectors are something that's completely on its own, but it's just that often the transition from vectors to other topics feels a bit alien, because with vectors you would think it's really just about space, about lines and planes, and you never really consider how it connects to other it's really difficult to bridge it back to other topics, although of course you can do that. So in this very first video, I don't want to overcomplicate things. I just want to focus on the problem and sort of the strategy of solving this kind of problem. And of course, we're still going to review some of the key ideas in vectors, all right? So today I took a question from, again, it's May 2010, higher level paper 1, and it's time zone 1. Okay, so it says, show that the two planes pi 1 and pi 2 are perpendicular, and it gives us two equations of the it gives us one equation for each plane. So one is x plus 2y minus z is equal to 1. The second one is x plus y is equal to -2. So let's see what we can do, all right? So because it's the least favorite topic of mine, we gotta use some fancy markers to do this, right? So I've got this blue marker, and I'm gonna use a very high-tech, actually, fountain pen to write this down, but let's give it a title. Let's say this is about the equation of a plane. How about that? Equation of a plane. All right? And we're gonna give it a date so that we can refer to this note later on. All right? Equation of a plane. Very nice. So, first of all, there are two things to recognize from this question. We gotta recognize the fact that it's the Cartesian equation of a plane. So, Cartesian equation of a plane looks like this. Of a plane, typically it's gonna be, this is your plane pi, let's say, and you're gonna have ax plus by plus cz equals to d. Well, without overthinking what this really means, it tells us two information, okay? It tells us, first of all, it's in three-dimensional space, hence you've got x, y, and z, and also it intersects the at point D, right? So the intersection is at point D between the plane and the axis. So which is to say, if you plug in x equals to 0, y equals to 0, and z equals to 0, you're gonna get D. Okay, let's sort of translate this and see what it actually means by first looking at a normal, let's say like an equation of a line, let's say, right? What you're really familiar with is the equation of a line. Let's say we have y equals to 2x plus 5, for example, okay? And then you could easily visualize what this looks like. It's gonna have a slope of 2, and it's gonna intersect at 5, right? So something that, okay, so maybe it looks something like this, right? And so it's the same idea, right? You can rewrite this equation, of course, as 2x minus y, right? You move y to one side equals to -5 or something like that. So basically, what this 5 really means, or the -5 really means, is that it's not an essential part of the equation. It really just pinpoints exactly where it's gonna be, because we've got an infinite number of lines with the same slope, right? 2x, for example, right? We could have, obviously, the line, I'm trying to use this fancy marker, okay? The line could be here, could be here, could be here, could be here. These are all lines with a slope of 2x, sorry, a slope of 2, and they intersect at various points, so we don't know where they are, in fact, right? So that's why we need that's when this 5 or this -5 here comes in handy, because then it pins the line down to a particular point, right? It says, in our case, it has to go through this 5 over here, for example, right? And so this D over here of the plane is the same idea, right? For a plane, you could have different kinds of we would call it slope maybe, but basically you would have a million planes that are parallel to each other, and the only way to distinguish the planes are the D, right? The only way to distinguish the planes is the D. I'm sorry. So if we know what this D in your line is doing for us, then we can think about the D that's in our plane. Okay. Another thing we can think about is, of course, well, what are the A, B, and C doing here in the plane? Well, first of all, we could go back to our equation of a line in two-dimensional space. Then we could see very easily that the AB of our equation of a line in this Cartesian form, what does it tell us? It tells us the slope, really, right? I would say it's the essence or the characteristic of the line. To me, let's say all of the green lines have slope equals to 2, let's say, right? And let's say I'm just having an excuse to use my fancy marker. Let's say we've got another type of line which maybe look like this, okay? Okay, so let's say all of these red lines have slope of, maybe it looks like -3, let's say, right? And there is this particular line with the equation y equals to -3x plus 5. So it has the same intersection on your y-axis as your as this line. Okay, so we got to think about what the slope is telling us. I think the slope is a much more essential quality than this 5 or -5 or the D, because the slope makes all of these lines really parallel to each other, but rather I would say that they make them into the same type of line, and I think that's a more essential quality than where it intersects with the x-axis or with the y-axis. So but if you don't like to compare the importance of the two different kinds of information, the thing you do have to know is that there are two things we can get from a Cartesian equation of a plane or of a line, right? First is the intersection with your axes, either your y-axis or x-axis or whatnot, and the other one is your slope, or the degree of slender, whatever you want to think about it, your slope or your gradient. I think British English it's gradient, no? Anyway, so the slope and intersection, these are the two things we want to look at, right? Where the a group of same lines could have the same slope, and because we want to distinguish all of these lines that have the same slope, what we do is to pin the line down by looking at the intersection with your y-axis. We just need to know one intersection, or we can look at the intersection with the x-axis. That's fine. All right. So two information needed. Let me write down. Okay. So in general, this is like informal language, but I think it helps us understand or visualize a little bit what exactly the Cartesian form of a plane is doing, right? So we have the slope, and the second is like, let's say location, or let's say intersection, okay? So if this is the idea, so this is, let's say, if I translate this, the slope tells us the quality, or rather the character, okay, of the line or the plane, and the intersection tells us the position, or let's say position, okay, the position of the line or the plane. All right, so there are two things. So let's go back to our plane. So the Cartesian equation of a plane looks like this: pi equals to ax plus by plus cz equals to d. So this one is our sort of the intersection, right? Or the position, okay, in informal language. And then A, B, C together, just like our 2 and -1 together, just like our 2 and -1 together tells us the slope. So for a plane, it's kind of a little bit different. What it tells us is the normal vector to the plane. So I'm going to circle our A, B, and C, okay? So all of these three, we're gonna be very fancy, and then we're gonna write it as this vertical vector form, okay? This tells us the normal vector of the plane. Okay, so the normal vector of the plane is what it gives us the character. It's the character of the plane. So let me highlight this a little bit. So two information gathered from our Cartesian and from our Cartesian equation of plane. Okay, one is the intersection or the position of the plane. The second one is the normal vector of the plane. Now, an interesting keyword here is, of course, the normal vector, right? So now then we have to go through a little bit of a philosophical idea behind this normal vector, right? So let's say we have a three-dimensional Cartesian coordinate. So we've got I would say z and y and x, but it doesn't matter how you label it, because it's on paper anyway. And suppose we have this plane that very beautifully looks like this, right? Something like that, right? How can we describe this plane? Again, when we look at the line, we describe it by looking at the slope, right? And we say that all of the groups of lines with the same slope, they behave almost. They are very similar in terms of their behavior, in terms of how we can predict things. For example, they have the same slope. It means that their first derivative will be the same, right? That's why we say the slope is a more essential property than the intersection, because it has to do with how fast the numbers are increasing, right? It has to do with the derivative. So the same thing with the plane, okay? So what is the sort of similar property to the slope? Well, if you think about if you think about a plane, often you would maybe use a piece of paper to represent the plane, and you use a pen to represent a line. That's all very creative, and sometimes it helps, but that's not very accurate, because after all, we have to remember that the Cartesian coordinate system is really just like a map. So, for example, when you're looking up a cafe, right, on maybe Google Map or something like that, it's not going to tell you how big the cafe is. It's just going to tell you where it is. So, if you have like a huge cafe located beside a tiny tree, to the Google Map system, they are all just one dot on the map, right? So the volume, let's say, or the size of your building is not gonna be represented on the map. So same with your Cartesian coordinate system. If you got a random point, we can only say that this is, let's say, 17, 2, and 5, and that's it, right? The dot doesn't have a size, okay, but no size, right? So same with your line. We could maybe give out the equation of the line, and it tells us, yes, it has this slope and it's going to intersect at the axis at this point. So we know the position and the character of the line, but again, we don't know it doesn't have any breadth, or it doesn't have any width, let's say. So the line is sort of, it seems like it's non-existent in a way that it seems like it's non-existent in the sense that it doesn't have any weight or dimensions, right? So that's a cool thing about math. It's unlike physics, where you gotta actually describe a lot of dimensions. In math, I really love this because it's totally abstract, and it's totally convenient to describe anything, and it's not going to discriminate between a huge fat dot versus a tiny dot. It doesn't matter, because really it's just a system to locate and to describe that line. So the only properties, or let's say the only property that matters is the slope. It's how the line or the plane is slanted, right? And then how fast or slowly let's say the variables are increasing or decreasing, right? How that affects the other variables. So a dot doesn't have a weight or dimension. A line doesn't have width or breadth or anything. And so similarly, a plane doesn't have thickness, okay? So that's why a paper is not exactly the best. It's not really close to the actual thing, because it's not a thing. It doesn't have weight. It doesn't have thickness. So, in fact, instead of describing the slope of this, so instead of representing the plane using maybe some crazy slopes like this, we have a much smarter way to represent it, which is to pinpoint the normal vector. Let me use a color. Okay, so The normal vector is, as you know, okay, I'm terrible at drawing, and this is probably not really accurate drawing, but basically normal means perpendicular, right? So it's the vector that is perpendicular to your plane. And I think that is super smart, and it's really cool because there are two things that this normal vector can do. First of all, it's going to tell you sort of the actual slope of the plane, let's say, right? If we know that this normal vector is 90 degrees to the plane, then we know that, okay, if its normal vector looks like this, then whatever the slope of the, or whatever the direction of the normal vector is, the plane will be 90 degrees from that normal vector. And another thing that it can do, I think, it's that it makes it more elegant, right? You don't have to it doesn't, the normal vector is just a vector itself. It has nothing to do with the intersection or the position of the plane. So basically it describes a whole group of planes that have the same normal vector, right? A whole group of planes can have the same normal vector, just like your whole group of lines can have the same slope, right? So I think the normal vector makes it very it's very neat, right? And the third thing actually that it's doing, it's reminding us, of course, that a plane cannot be pinpointed by its own slope kind of thing. We really just care about a group of planes that have the same normal vector. All right, so that's kind of a big derailing from the actual question. I'm just here to remind you what the Cartesian equation of the plane tells us, right? So this is the key information here. In a Cartesian equation of a plane, we've got A, B, and C, and we can rewrite A, B, and C as this, as a vector form. It is the normal vector of the plane, which is to say, it is the vector that is perpendicular to the plane, which of course has no height, no length, no thickness or whatever, and so the normal vector gives us only the essential characteristic of this plane. And then if we want to know where the plane is actually located, we want to pinpoint the plane in our Cartesian coordinate system, then we gotta know also where it's gonna intersect when we are given a particular point on the plane, let's say x, y, and z, right? If we have A, B, and C, and we also know we want to know a particular point where that point is going to be on the plane, then we have to plug in the coordinate of the plane, the coordinates of the point, and then we plug in x, y, and z, and then we will get a particular number. That's how we can find that point on the plane, something like that. Right? So again, just like a line, you've got slope and intersection. So in a plane, we can also have a Cartesian representation of the plane where we have the normal vector and the intersection. Okay, I think it makes it very clear what this thing is about. So we go back to our original question, right? The question says, so we've got two planes. The first one is x plus 2y minus z is equal to 1. Pi 2 is x plus z equals to negative 2. So now we want to show that they're perpendicular, and that's a key word, which is to say we want to know how their normal vectors are behaving. Okay. Well, now if you recall, or actually you don't have to recall, you actually just need to look at the data booklet, right? If you check your data booklet, it's a AHL 3.13 data booklet. Let me write data to remind you, data booklet, and it tells you that I think cosine of theta is vector A dot vector B divided by the magnitude of A and B, right? So what this equation says is that the angle between two planes is, the angle between two vectors is theta, and cosine of theta is going to be the dot product, right? This is our dot product or the scalar product, okay? And then divided by the what is it called? The magnitude multiplied together. Okay, so what this equation tells us is, okay, what we can do with this information and with this equation is, first of all, we can extract our normal vector from here. So we already know it's gonna be 1, 2, and -1, right? Where 1 corresponds to the x, and then 2 is the y, and then z is the -1, and then this is the normal vector, okay, of the plane. And for this one, it's gonna be 1, 0, and then 1. Okay, so we have the key information of these two planes, and then if you think about this, right, so we can just ignore really the fact that the normal vector is 90 degrees to the plane. We could just think of it's the same thing as telling us the slope of the plane, because because we are trying to prove that they're perpendicular, right? So let's say there's this plane A, and the normal vector looks like this, and then there's another plane B, and let's say this is B normal vector, A normal vector, and this is B normal vector, which means B must be this, right? So this is, I'm terrible at drawing. This is our B, this is our A, right? If the normal vectors of the two planes are perpendicular, then the planes themselves would also be perpendicular. You would just imagine that plane A would have the same direction as the normal vector of plane B, and plane B would be in the same direction as the normal vector of A, right? So that's why our marker comes in handy, so we can group the things that are parallel together, right? So normal vector of plane A will be the same direction as normal vector of plane B. Normal vector of plane A is going to be the same direction as the plane B, and then plane A is going to be in the same direction as the normal vector of plane B, right? So if we want to describe what's going on here, we could say normal vector of plane A, and then plane A, and we could draw a table, maybe normal vector of plane B, and then plane B, right? Normal vector of plane A and our plane B, these two are going to be, based on our diagram, they're going to be same, right? Same direction. And then normal vector of plane B and normal vector of plane A, well, they're going to be perpendicular, so we use a symbol for perpendicular. And normal vector of plane B and A, they're the same. So planes A and B themselves, they're also going to be perpendicular. Which is to say, of course, that if the normal vector of A and B, which is the information we have, are perpendicular, then we can say that the planes themselves are also perpendicular, right? A and B are also going to be perpendicular. So that's great. That's why we love the normal vector. It tells us it's useful enough for a lot of things. Well, be careful. This actually only works because we're looking for the perpendicular property, right? If it's not perpendicular, then it's going to be a little bit tricky. You got to consider 90 degrees minus whatever theta you've got. But in our case, in the case of perpendicular, they're going to be the property is going to work perfectly. So we just have to consider if the normal vectors themselves are perpendicular. Now, how can we look at the angle between the normal vector, we go through this formula, right? So our formula says cosine theta, which is the angle between, I just want to circle our nice formula. You know, I just really want to use my marker. But let's say, if we want to look at the angle between the normal vectors, we gotta find their dot product. And when our if the two vectors are perpendicular, what do you think the angle between them is going to be? Well, by definition, if they're orthogonal or perpendicular, it means that it means that their degree is going to be pi over 2 or 90 degrees. Okay, so if two vectors are perpendicular, then theta would be pi over 2, and what is the cosine of pi over 2? Cosine theta would be 0, right? And so if we go back to this, which is to say that if dot product of the vectors would be 0, right? So we don't really care. First of all, we don't care about the magnitude, because magnitude, unless you're a 0 vector, otherwise your magnitude is not going to be 0. So the denominator cannot be 0 anyway. So we only care about their dot product, which is A dot B, right? So this is very important. If we want to know if two vectors are perpendicular, what we need to do is to take the dot product of the two vectors and figure out and see if it's equal to 0. So if it's equal to 0, then we can say that they're perpendicular. All right. So how do we find the dot product? Dot product. By the way, it's also called the scalar product, which is to say it doesn't have any vector component. So after you take the dot product, you get a real number, right? You have no vector component. Let's say A1, A2, A3 dot B1, B2, B3 is just A1, B1 plus A2, B2 plus A3, B3. All right. So if this product is equal to 0, then we can say that the two vectors are perpendicular. Okay, so going back to our example, let's check. So dot product of our pi 1 and pi 2 is what? Is equal to 1, 2, negative 1 dot 1, 0, 1, which is this is what? 1 times 1 is 1, right? 1 times 1 is 1. And then plus 2 times 0, which is 0. And then plus negative 1 times 1, which is negative 1, which is 0. Which is to say that cosine theta is equal to 0. Which is say cosine theta is 0, which means theta is equal to pi over 2. Which means pi 1. Technically, their normal vectors are perpendicular, but as we've seen, if their normal vectors are perpendicular, the planes themselves must also be perpendicular. Are perpendicular. Okay. So again, this question is very straightforward. It really doesn't. It has very little calculation. Okay, so in fact, when you're trying to write this on an exam or something, you don't need to write these two lines, because this is sort of common sense. All right. So the idea is that if the dot product of two things are 0, then they're the two vectors are perpendicular. Okay. And then technically it's the normal vector, okay, of pi 1 and pi 2 are perpendicular. But we've seen in our case here that we could consider the fact that they're perpendicular here means that they are perpendicular here. Okay? So that's our question 1. I'm sorry that it took so long, but it's just that vector, once you get the sort of the picture literally behind the question, it's super straightforward, right? You just try to find the dot product and you will get a result. Okay, so the essence of this question is really finding the dot product of two. Well, really, it tests you the Cartesian equation of the plane, and then asks you try what is the normal vector of the plane, and then you gotta try to find the dot product of these two of the normal vectors of the plane and test if the normal vectors are perpendicular. And if they are, we would say that the planes themselves are also perpendicular. Okay, so technically that's what is going through. Okay, the second part of the question, okay, is this: find the equation of the plane, another plane, pi 3, which goes through the origin and it's perpendicular to both pi 1 and pi 2. So again, let's go back to our beautiful notes. So for every kind of thing on your Cartesian plane, there are two things we want to know, right? We want to know its position and we want to know its character. By character, I mean either the slope or the normal vector in case of a plane, right? So in my notes, so in the question, it says basically we want to know two things: where it is, so it passes through the origin, so it means that it goes through the point 0, 0, 0, and the character of the plane is such that it is perpendicular to both of them. Okay, so two information for every single plane: normal vector and a particular point. Right? So this is again character and position. Okay? I like to think of it that way because it makes so much sense. Okay? Then you would see how the Cartesian equation of the plane really works. So we already know that for this particular plane pi 3, it passes through the point 0, 0, 0. We know the answer to this already. Alright? So the only thing we got to know is its normal vector. Okay? So this is to say if we want to know the d of the Cartesian equation of the plane, b y plus cz equals to d. If we want to find out the d, we just need to plug in 0, 0, 0, and so d would definitely just be 0. Okay, so d is gonna be 0. Okay, d is 0. Okay, I bet just by writing this down, you would get 2 marks already. But finding the normal vector, a keyword in this question, perpendicular to both pi 1 and pi 2, that makes me so happy. So as we said, we got the scalar product, which is where the product only produces a real number and not any vector. We've got another product, which is the cross product. Okay, the cross product or the vector product, it's gonna be cross product of vectors, let's say A and B, is a vector, let's say C, that is perpendicular to both A and B. Isn't that wonderful? So basically we just need to find the cross product of our normal vectors A and B, our normal vectors of planes 1 and 2. Then we will get a normal vector, a vector that is perpendicular to both planes, which will be a normal vector to plane 3, right? So if we take a look at the picture here, let's say this is our vector A and we have a vector B. If we take the cross product, it's gonna produce a vector C. Okay, I don't know why I need to use, okay, it's like a full one. Okay, it's gonna produce a vector C where it's gonna be 90 degrees here. It's also gonna be 90 degrees here. So in a way, if you want to look at the three-dimensional, it would be where, right? This is B and this is A, and then C would look like this, right? It would just go out of the plane. So it's gonna be the normal vector of the plane, which contains both vectors A and B, right? Something like that. So that's the idea. And C is gonna be, so in representation we say A cross B equals to C. Okay, this is how we write it down. Okay. So what was our question? What was our vector? Okay, so basically if we have A, which is 1, 2, and -1, cross our 1, 0, and 1, okay? This is our plane 1 normal vector, plane 2 normal vector, okay? Now, how can we find the cross product? That's where the data booklet really comes in handy. This is one of the things where I really don't like to memorize, but the basically, if you do it multiple times, you remember the first layer. You gotta look at this part. Okay, so the cross product here is literally you cross it, so you got to do 2 times 1 over here, and minus 1 times 0. Okay, so you gotta do 2 times 1 minus 1 times 0. Okay, and then the second part is gonna be the green part. So let me do this. Okay, so rule 2, 3, and then rule 1, 3. Here it's 1 times 1. Oh, sorry. See, I always mistake this. Sorry, 3. It's -1 here. -1 times 1 minus 1 times 1. Okay, and then finally you do the top 2 rules. Okay, so top 2 rule is 1 times 0. Subtract 2 times 1. 1 times 0, subtract 2 times 1. Okay, so this is gonna result in 2, -2, -2. Okay, and that's it. Okay, so I think I wanna review a little bit what this cross product formula is. I hope I remember it correctly, but let me highlight. This is the first one is rule 2, 3. The second one is rule 3, 1, and the third one is your blue part, which is the rule 1, 2. Okay, so this is what you are gonna result in. Let's double check maybe with our data booklet. So technically, what the formula really says is this. Okay, let me write it down. Okay, so we have, let's say, A1, A2, A3 cross B1, B2, B3 is equal to the 2, 3, right? A2, B3 minus A3, B2, okay? And then the second one is going to be A3, B1 minus A1, B3. A1, 3. I was right. And the last one is going to be A1, B2 minus A2B1. Okay, so that's the general equation. So you can take a look if I got anything wrong. I think this is fine. Okay, so what have we got then? So what have we got is the fact that we have produced the the normal vector of your plane 3. So putting this back into our Cartesian equation, we have 2x minus 2y minus 2z equals to 0, because we already know it crosses through the origin, and this is also just the same as x minus minus y minus z equals to 0. Okay, so this is gonna be the equation of the plane. This is pi 3, right? Okay, so that's how we get the equation of our plane. Okay, so this is normal vector. Okay. All right, excellent. So we've got our question completed. Okay, so this question really, I don't understand why I thought it's vector, which I hate, and I could produce such a long video. But the general, so let me put down the answer here. Show that A, briefly speaking, a scalar product is 0. The second thing is cross product is equal to normal vector. Passes through origin, which means passes through 0, 0, 0, right? So that gives you the position of the plane. Okay, so that's very nice. So we have the whole question done. So last comment, it's just that basically the general property of any plane or any line is that it has a position, it also has a particular slope, or in the case of a normal vector, you've got a normal vector. Sorry, in case of a plane, you've got a normal vector. All right, so I hope this is clear enough. All right, so I'm going to turn this off, and we see you in the next video. Bye bye.